This is my Precalculus course. Today we're going to learn how to solve nonlinear inequalities. If you haven't done the homework completely incorrectly from the last class, do that homework before watching this video. First, we're going to review linear inequalities. We learned these in my pre-algebra course. So we're going to solve these the same way we would an equation. Let's simplify first. Then we'll subtract 6 from both sides and multiply both sides by 2. And we have our algebraic solution. This tells us that x can be any number as long as it's greater than 12. Be aware that you can flip this inequality around and it means the same thing. That's the algebraic solution. Now let's draw the graphical solution. Solutions, actually plural, there's more than one solution. So x is greater than 12, so we're going to shade to the right. And we use an open dot because x cannot be equal to 12. If this symbol were a less than or equal to symbol, then we'd have to have a closed dot there. So we have the algebraic solution, and let's rectangle the graphical solution. Let's try another one of these. We'll subtract 10 from both sides. Again, we solve just like we would an equation. And now we're going to divide both sides of the inequality by -4. But notice that I flipped the inequality. We had less than or equal to symbols, and I switched to a yellow greater than or equal to symbol because whenever you multiply or divide both sides of an inequality by a negative number, when you multiply or divide by a negative number, you have to flip the inequality. So that's very important to remember. That's the algebraic solution. Now the graphical solution. We're going to draw a closed dot because the symbol is greater than or equal to. And then we're going to shade to the right. And that is the graphical solution. So x can be any number that is greater than or equal to 9/4, and if you plug it in to this inequality, the inequality will be true. But if you plug in any of these orange numbers that are less than 9/4 into this purple inequality, the inequality will not be true. So this is what it means to find the solutions of an inequality. So we're going to simplify here, and then we'll subtract 4x from both sides, and that is the algebraic solution. And now the graphical solution, we want a closed dot because it says x is less than or equal to, and we're going to shade to the left because the x values can be anything less than or equal to 7. So there you go. And now I want you to try some of those problems. So go ahead and attempt number 4. And when you come back, we'll do it together. Alright, we're back. So we're going to subtract 1 from both sides of the inequality. Then we're going to multiply both sides by -5. And notice that I flipped the inequality. We had greater than or equal to symbols, but then we switched to a less than or equal to symbol because I multiplied both sides of the inequality by -5. So that's the algebraic solution. Now the graphical solution, we need a closed dot because it's less than or equal to, and we're going to shade to the left. So if you got those answers, good. So the problem's asked to find the algebraic solutions and the graphical solutions. Okay. Go ahead and try number 5. When you come back, we'll do it together. Alright, we're back. So I'm going to subtract 4 from both sides and add 2x to both sides. Then I'm going to divide both sides by 3. And that is the algebraic solution. And now I'm going to draw the graphical solution. So if you got those answers, excellent. Now in this case, we divided by a positive number, positive 3, so we do not flip the inequality. Okay, go ahead and try number 6. When you come back, we'll do it together. Alright, we're back, so let's simplify the right side of the inequality first. 4 minus 6 is negative 2. Add 2 to both sides. And divide both sides by negative 3. And notice that we changed the green greater than symbols to a blue less than symbol because we divided both sides of the inequality by a negative number. This is the algebraic solution, and now the graphical solution. We need an open dot, and x is greater than, so we're going to shade over here. So if you got those solutions, excellent. Okay, so today we're going to use a lot of factoring methods, and it can be a little confusing to have to keep track of all the different types of factoring that we're going to be doing. In my curriculum, at some point, you've learned all of these types of factoring methods. But I want you to take a picture of this. This is factoring that you're going to be using throughout your entire math education. So get a picture of that with your phone. And these are the steps that we're going to follow to solve nonlinear inequalities. But it's easier to just show you what to do rather than to read these steps here. But I do want you to take a picture of these steps with your phone. So go ahead and do that. And now we're going to solve nonlinear inequalities. This is a nonlinear inequality because we have an x squared term. It says write the solutions graphically and in interval notation. Now in the previous problems we used inequality notation, which in this case for these problems would have to be used with set notation, but it's kind of tedious to use set notation and inequality notation for these nonlinear inequalities. So we're going to switch to interval notation just because it's more convenient. We learned about set notation and interval notation in my intermediate algebra course. So we're going to find all of the x values that would make this inequality true. What are the x values that we can plug in so that this side really is greater than or equal to this side? Well, we don't know. It's too difficult to figure it out. But if we put everything on the same side, the problem is going to become much easier to deal with. Now, I put everything on the right side because I want this leading term to be positive. That just makes things easier. So that's always step number 1. Step number 1 is to put everything on one side of the inequality and make sure that your leading term is positive. Okay, so that's step number 1. Move all of the terms to one side of the inequality. At this point, we're going to consider the graph of this equation. Let's say that we're going to graph this. Well, we know what that looks like. That's a parabola. And it's going to look something like this. Not exactly like that, but something like that. Let me draw that a little better. Something like that. And the reason that we put everything on one side is because now the problem becomes very easy for us to understand. We're trying to figure out all the x values that would make this expression less than or equal to 0. But because we have the graph of the expression down here, we can see that that expression is going to be less than 0 for these x values here because the graph is under the x-axis. It's below the x-axis. So that's what we're going to be doing here. But notice that the graph changes at these x-intercepts. The y values change from positive to negative or negative to positive at those yellow x-intercepts. So those x-intercepts are where signs change. So that's going to give us kind of our boundaries. So we need to find where those x-intercepts are going to be. So in order to do that, we factor. And we get the following expression. So what this tells us is that x, if x is 3, then we have 0, and if x is negative 9, we have 0. That's these two x-intercepts. So what we're going to do is make a sign chart. We're going to mark negative 9 and positive 3. And if you plug in a value here, like 0, you see that the graph is below the x-axis. So the sign of that region would be negative. If you plug in 4 to test this region, and you can plug it into here, but it would probably be easier to plug it into this expression down here. You get 13 times 1, which is positive, so we'll make that positive. If you plug in negative 10, you get a positive number. Plug in negative 10 to here. So throughout the class today, we're going to be drawing these sign charts. The good news is we don't have to graph every expression, because that would be very time-consuming. So now that we have the sign chart, now we can write the graphical solution. So we're going to write closed dots because it's a greater than or equal to symbol. And we want to know where this expression, in other words, the blue y values of the graph, we want to know where that blue expression is less than 0 or equal to 0. Well, that's this inner part here where it's negative, where the y values are negative. Very important to understand that the y values of the graph are the values that you get when you plug in x to this expression. The y values are this green expression after you calculate all the numbers. So this is the graphical solution. If x is any number between negative 9 and 3, then this expression is going to be less than or equal to 0. But x can be negative 9 and 3 also, because that would make this expression exactly equal to 0. So the reason that we put everything on one side is then the problem just becomes an issue of finding where the expression is positive or negative. But we have a lot of experience doing that because we know how to factor and find the zeros. So that's how every problem is going to work today. But notice up here it says to find our answer in interval notation also. So we're going to write the answer in interval notation. Let me move this up here. In interval notation, the answer would have brackets. So we go -9 to 3 with brackets. And there you go. The reason we use brackets is because we have closed dots here. It says less than or equal to. So we need brackets there. Okay, let's try another one. Notice that we factored a quadratic expression. Now we're going to factor the difference of two squares. First step is to put everything on one side. Remember, always put everything on one side. We want the leading coefficient to be positive. Then we're going to factor the difference of two squares, which is something that you're familiar with at this point. Then we're going to make a sign chart. Now we don't have to graph. We can just make a sign chart. And if we plug in 0 into this expression, we get a negative number. If we plug in 11 to this expression, we get a positive number. I'm just using test numbers. And if we plug in -11, we get a positive number. And the multiplicity of each one of these zeros is 1, which means that the sign has to change. Remember, if you have a multiplicity of 2 or a multiplicity of 4, then the sign doesn't change at these zeros. This 0 would be 1, this 0 would be -5. But if you have another factor, say x plus 3 to the 5th power, the sign is going to change there because it has an odd multiplicity. The multiplicity of these factors is 1, so that's an odd multiplicity, which means that if zeros do exist, then you're going to have a sign change. And we show that the zeros do exist, the signs change. So in other words, you don't have to necessarily test each region. You can know just by looking at the multiplicities whether or not the sign is going to change. So we're trying to figure out when this expression is greater than 0. And by the way, we don't have to write open circles for the sign chart. We don't really care about that. We'll write the open circles down here. We want to know when it's greater. The expression is, we want to know when it's greater than 0, and that's going to be the outer regions here. We're going to shade in these outer regions. So that is the graphical solution. And the solution in interval notation is going to be -∞ to -10 union +10 to +∞. So whenever you have a gap, you have to use a union symbol. Now we don't use brackets because, again, we have open circles. It's a greater than symbol, not a greater than or equal to symbol. So we factored a quadratic expression, then we factored the difference of two squares. And now we're going to do some more factoring here. So again, step number 1 is to put everything on the same side. And then we're going to find the values that will make this expression equal to 0, because that will tell us when the sign is going to change. So we're going to factor out a GCF, which is something we haven't done yet today. That's another type of factoring, factoring out the greatest common monomial, or the greatest common factor. So we factored out the GCF, which is 2x, and now we're going to factor the quadratic left inside. Actually, I need to change the signs there. There we go. So we don't have to graph this expression to see where the y values are less than 0. We can just do a sign chart. So we have -1, we have 0, and we have 1/3. So I got the 1/3 from there, and I got the -1 from there, and the 0 from there. So if we plug in, let's try plugging in 1 to test this region. We get 2 times 2 times 2. So that region is going to be positive. And the multiplicity of each one of these zeros is 1, because the exponent for all these is 1. So that means that there's going to be a sign change at every 0. So we're going to have a negative region, and then another positive region, and another negative region. But again, you can choose values in these intervals and plug them into this expression to verify that the sign of the expression is going to be what we wrote. So this tells us where the inequality is less than 0. It's where we have the negative symbols. So we're going to need open dots. And looks like it's going to be this region here and this region here. Your spacing doesn't have to be perfect. That's not really the point of this. But that's the graphical solution. Now let's draw this. So write the solution in interval notation. So there you go. Okay. So let's try one more of these problems before you try one on your own. We have factored out a greatest common factor. We factored a quadratic expression, and we factored the difference of two squares. Now we have this special form that kind of resembles a quadratic expression. So we're going to factor. It works just like a quadratic. It's not a quadratic, but it works just like a quadratic. We've seen these before. And it looks like we're going to have -4 and -9. But now we have the difference of two squares. Now again, remember, you want to start by putting everything on one side. That's always the first step. And then we're going to factor the difference of two squares. So we have the difference of two squares here, and we have the difference of two squares here. So now we can make a sign chart. And the multiplicity of each one of these zeros is 1, so that means there's going to be a sign change at each one of these values. Okay, so let's try plugging in 0. We can plug that up here, and we get +36. So So that region is going to be positive. This expression is going to be positive in that region. And again, now that we know the sign of one region, we can figure out the sign of all the other regions, because the signs have to change. But again, you can test points. You can test negative 2.5 by plugging it in here, see if it's less than or equal to 0. You can plug in 2.5 to test this region. You can plug in 4 to see if it's positive or negative, so on and so forth. Okay, so now we can write the graphical solution. We need closed dots. We want to know where it's less than or equal to 0, so that's going to be this region and this region. So that is the graphical solution. And let's write the solution with interval notation. We're going to need brackets and a union symbol. So that is the solution using interval notation. Okay, so if you haven't gotten a picture of all this, take a picture with your phone, and I want you to try number 11. Start by putting everything on one side of the inequality. You want to put it on the left side, everything on the left side, because you want x squared to be a positive term. Then you're going to factor, write a sign chart, and write all the zeros on the chart, and figure out where the expression is going to be positive or negative. Try number 11. When you come back, we'll do it together. Okay, we're back. So again, the first step is always to put everything on one side of the inequality. Then we're going to find the zeros. By factoring. And now we know what the zeros are, and the zeros are where the sign is going to change. And if we plug in 0 to test this region, we get negative 15. So we know that region is going to be negative, and the multiplicity on each 0 is 1. That's an odd multiplicity, so that means the sign is going to change. But again, you can plug in 4 and see that it's going to be a positive number, and you can plug in negative 6 and see that this is going to be a positive number. So now we're ready to write the graphical solution. And you don't have to write dots on the actual sign chart. We can just write tick marks. We want to know where the expression is greater than or equal to 0. So that's going to be these outer regions where we have the plus sign. And there you go. So that's the graphical solution. Now let's write the solution in interval notation. Whoops. That's not right. We have to start with a negative infinity symbol. Always write a parenthesis on an infinity symbol. Always write a parenthesis on the infinity symbol. But we need brackets because it's a greater than or equal to symbol. Okay, so if you got that one right, good. You can take a picture of these problems if you'd like to help you with number 12. I suggest you do that. Take a picture with your phone. And I want you to try number 12. Remember, the first step is to put everything on one side of the inequality. And you want this term to be positive, so you're going to put everything on the left side of the inequality. Now you're going to have to factor the difference of two squares in this problem to find your or to write your sign chart. So try number 12. When you come back, we'll do it together. Okay, we're back. So I'm going to put everything on one side of the inequality. Then I'm going to factor the difference of two squares, which is something that you should be used to by now. And now we can see the zeros. The zeros are -5 and 5. And we want to know where this expression is less than 0. Actually, we only need tick marks. So if we plug in 0 to test this region, we get -25. So that's going to be a negative number. And we have a positive and a positive. Plug in 6, and we get a positive number. Plug in -6, we get a positive number. So we're testing the signs of each region. So that allows us to write the graphical solution. And we want to know where the expression is less than 0, so that's going to be the region where the y values of the corresponding graph are negative. And so that is the graphical solution. Using interval notation, we need parentheses. Now, the reason we use parentheses is because we have open dots. If they were closed dots, we'd use brackets. So if you had a little trouble with that part, with the parentheses, that's fine. Now you know that we use parentheses when you have open dots. So you got that right. Good job. Go ahead and try number 13. I'm going to give you one more chance to take a picture of all this factoring and these previous problems if you haven't already done that. Try number 13. And when you come back, we'll do it together. Remember, start by putting everything on the same side of the inequality, and you want this term to be positive. All right, we're back. So I'm going to put everything on the right side of the inequality. And then I'm going to find the zeros by factoring. So we're going to factor out an x, and we have 2x squared minus 15x plus 18. Now we have a quadratic expression, so I'm going to factor that also. And I'm going to try +3 and -6. Actually, both signs have to be negative in this particular problem because they multiply to a positive. Okay, so this allows us to see the zeros. So we have 6, we have 1.5 or 3/2, and then we have 0. The spacing doesn't have to be perfect. So I got my 0 from there, I got my 3/2 from there, and I got my 6 from there. Okay, so let's plug in some numbers. If we plug in, let's try plugging in 7 to test this region here. We get 7 times 14 minus 3 times 7 minus 6. That's going to be a positive number. And again, the multiplicity of each one of these zeros is 1, so that means the signs are definitely going to change in each region. We will have some problems where the multiplicity will not be 1, but we're not doing those problems yet. So we want to know where this expression is going to be greater than or equal to 0. So that's the positive regions. We need closed dots because it's a less than or equal to symbol. And so we're going to shade in the positive regions. And that is the graphical solution. We're going to need brackets for the interval notation. We have 0 to 3/2, including 0 and 3/2, and then we have 6 to positive infinity. And remember, never write a bracket next to an infinity symbol. So that is the solution in interval notation. If you got that right, excellent. Okay, so go ahead and try number 14. And when you come back, we'll do it together. Remember, we always start by putting everything on one side of the inequality, but you can see that everything is already on one side of the inequality, so you don't have to worry about that. So the next step is to factor. Go ahead and try 14. When you come back, we'll do it together. Alright, we're back. So I'm going to factor. And it looks like it's going to be -1 and -25. And so now we have the difference of two squares with one of these factors and the difference of two squares with the other factor as well. So we factored the difference of two squares here and the difference of two squares here. And that allows us to see the zeros, and the zeros are where the signs are going to change. Again, the spacing doesn't have to be perfect. So let's test 0. That's the easiest number to test. We'll test this region by plugging in 0, and we get a positive 25. So that region is going to be positive. The multiplicity is odd multiplicity. So that means the signs are going to change at every 0. So now we can write the graphical solution. We want this expression to be greater than 0, so that's where it's positive. So that's all these regions here. So that is the graphical solution. And now we're going to write interval notation, so -infinity to -5 with a parenthesis because it's an open dot. Union symbol, -1 to 1 with parentheses because they're open dots. Again, we need another union symbol, 5 to infinity. And there you go. So if you got that one right, excellent. So let's try these next problems together. Again, first step is to put everything on one side of the inequality. And then we're going to factor. Now what's different about this is this 0 here has a multiplicity of 2 because you can put these together and you see that the exponent is now 2. That's an even multiplicity, so that means that the sign of this expression is not going to change at that 0. So to demonstrate that, we'll do a sign chart and we'll write 9/2. And if you plug in, let's try plugging in 0 to test this region. We plug in 0 and we get positive 81. Now this is about 4.5, so we can plug in 5 to test this region here. So let's plug in 5. It's kind of hard to do that up here. So we can plug in 5 here and we get 1 times 1, which is positive. So you see the sign didn't change. So our answer is going to be something interesting. Let's write the graphical solution. We want to know where this expression is less than 0. Now, it's greater than 0 in these regions here because the sign is positive. When you plug in 9/2, you get 0. This expression becomes 0. But we want to know the x values that make it less than 0. Well, it turns out there are no x values that do that. So the answer is no solution. Again, if you plug in values in these regions, you get a positive number, but that makes the inequality untrue. We want it to be less than 0. If you plug in 9/2, it equals 0, but again, we don't want the x values that make it equal to 0. We want it less than 0, so there's no solution. So that was kind of a tricky problem. So let's try this next problem together. This is going to be a similar situation. Something strange is going to happen. So everything was already on one side of the inequality, and I factored. And notice that those two factors are the same, so that means the sign is not going to change necessarily. So the 0 is -1/7, and let's test this region. Actually, let's test this region. Let's plug in 0. We plug in 0, we get +1. So that region is positive. And if we plug in, say, -1, we get a negative number times a negative, which is a positive. So we want to know where this expression is less than or equal to 0. Where is it less than or equal to 0? It's not less than 0 when you plug in these x values, because these x values would make the expression a positive number. It can't be a positive number. It's got to be a negative number, or it's got to be 0. If you plug in -1/7, this expression becomes 0. So that's actually the only solution. You could write x is equal to -1/7, and that would be your answer. But we're used to using a graph to show our solution, so the answer for this one would just be a dot, a closed dot, and that's it. If we write interval notation, it's not very common to use interval notation for just one number, but if you had to use interval notation, it would look like that. The reason we don't use interval notation is because it's not an interval. It's just one number. But just to keep things consistent, we'll write the answer in interval notation as well as graphical notation. So you can see in those situations it was kind of weird. Something weird happened. For number 17, something strange is going to happen. Try number 17, and when you come back, we'll do it together. If you get stuck, that's okay. Okay, we're back. So we're going to start by putting everything on one side. And then we're going to factor so we can see the zeros. And this expression has, well, the 0 has a multiplicity equal to 2. If we write it in exponential form, we can see the multiplicity is 2. So that means that the sign is going to, the sign is not going to change at that 0. So let's try plugging in 0, and we get +9. Let's try plugging in 4, and we get +1. Again, you can plug in your number here or here, whatever's easier. So as we predicted, the sign didn't change. So we want to know where this expression is greater than or equal to 0. So that would be all the x values here, all the x values here, and it would be this x value, because this x value makes it equal to 0. So if you're going to graph the solution, it would just be all real numbers. It's not typically a way we'd show the solution, but you would just shade in everything. And for interval notation, we can say negative infinity to positive infinity. So if you weren't quite sure how to do the interval notation in this case, that's okay. I kind of tricked you with that problem. I gave you one that we hadn't done yet. So if you had a little trouble there, that's okay. But we have seen this interval notation in previous courses. So this just means all real numbers. And remember, we always use parentheses next to infinity symbols. But if you had trouble with that, again, that's okay. Go ahead and try number 18, another strange problem. And when you come back, we'll do it together. Okay, we're back. So everything's already on one side of the inequality. So we're going to factor. And factoring will allow us to see the zeros. So there's only one zero in this case, as in the previous problems, and that's going to be negative 6/5. So if we plug in 0 to test this region, we get a positive number. If we plug in negative 2 over here, we also get a positive number. And if we plug in negative 6/5, of course, we get 0. So we want to know where this expression is less than or equal to 0. It's not less than 0 when you plug in these x values in these regions, because we get a positive number, so it's not going to be less than 0. But when you plug in negative 6/5, it's equal to 0. So that's the only x value that would satisfy this inequality to make it equal to 0. We cannot make it less than 0, but we can make it equal to 0. So we're going to have a closed dot, and that's it. That's the only x value that we can plug in. So again, it's not very common to write interval notation for something that's not even an interval, but if you had to do it, it would look like that. So if you got that one right, good job. Okay. So now we're going to do problems that require the Rational Zeros Theorem. So remember, begin by putting everything on the same side. And we want to find where this expression is equal to 0, so we have to factor, but the problem is it's a difficult expression to factor. So we're going to have to use the Rational Zeros Theorem. P is 12, Q is 1. So I got that from there, and I got that from there. This is all just review for you. So the factors of 12 are 1, 2, 3, 4, 6, and 12. And the factors of 1, of course, are 1. Then we divide all the factors of P by the factors of Q, and we get plus or minus 1, plus or minus 2, plus or minus 3, and we don't have to write all of them. Let's try plugging in 1. We get 1 plus 1 is 2, minus 8 is negative 6, minus 12. That doesn't work. It's not a 0. We're trying to figure out the values that will make this expression equal to 0. Let's plug in negative 1. We get negative 1 plus 1. And then 8 minus 12, that doesn't work. So let's try plugging in 2. We get 8 plus 4 is 12. Minus 16 is negative 4. Minus 12, that doesn't work. So let's plug in negative 2. We have a negative 8 plus 4 is negative 4. Plus 16 is 12. And 12 minus 12 is 0. So that works. So we tried 1. That didn't work. We tried negative 1. That didn't work. And we tried 2. That didn't work. And we tried negative 2. And that did work. Okay, so now that we know negative 2 is going to work, we can use synthetic division. We're going to divide x cubed plus x squared minus 8, minus 8x that is, minus 12. We're going to divide this polynomial by x plus 2. And we're going to do it the fast way using synthetic division. The remainder is 0, so that suggests we did it correctly. So what I'm going to do is I'm going to change this green expression. I'm rewriting the inequality, but I'm going to rewrite it as x plus 2 times the purple x squared minus x minus 6. That's less than 0. So all I did was just rewrite the expression. So now we can factor the remaining part. We have negative 3 and positive 2. And so now we have a 0 that has an even multiplicity because I can put those x plus 2's together. So that means that the sign is not going to change at negative 2. Because this is even multiplicity, whereas this is odd multiplicity. So the sign is going to change at this 0, but it's not going to change at that 0. So let's see what happens. Let's plug in 0 and test it. We can plug it in here. In this case was 0. It's probably easier to just plug it in up here. And we see we get negative 12 when you plug in 0. So if you get a negative number, that's going to be negative. And the sign doesn't change at negative 2, so we know that's just going to be negative again, but the sign does change at 3. Now, again, if you don't believe, you can plug in negative 3 to this expression, test it, and again, you can plug it in there, or you can plug it in up here. It doesn't matter, whatever's easier. Because again, this expression up here is the same as these expressions here. It's the same values, just different forms. You can plug in 4 and verify that this expression is going to be positive. But again, you can use multiplicity to help you find the signs. So we need open dots, and we need to know where the expression is less than 0. So this is going to be a little tricky here. So we do have a region here where the expression is negative, so it's less than 0. But here it's equal to 0, so that number doesn't count. But this region over here does count. So that was kind of a tricky problem. So we have the graphical solution there. I'm going to rectangle that. And now let's draw the interval notation. So we're going to have negative infinity to negative 2, union negative 2 to 3, and there you go. So this means that x can be any value between negative 2 and 3, but not equal to negative 2 or 3, and it can also be any value that is less than negative 2. Okay, so it's time for you to try a problem like that. You can use number 19 to help you. Go ahead and try number 20, and when you come back, we'll do it together. Okay, we're back. So I'm going to draw a divider here. We start by putting everything on one side of the inequality. And we're going to have to use the Rational Zeros Theorem to help us. So we have 6 and 1. So 1, 2, 3, 6 are the factors of P. Factors of Q are 1. So we have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. You don't have to write all of them. And by the way, you don't have to write this. You can do it in your head. Just try 1, try negative 1, try 2, try negative 2. So let's try plugging in positive 1. We get 1 plus 4 is 5, plus 1 is 6, 6 minus 6 is 0. So 1 actually works. So we got lucky on that one. So we can use synthetic division, and we're going to divide x cubed plus 4x squared plus x minus 6 by x minus 1 using synthetic division. So let's do the algorithm. 0 is the remainder, so that's a good sign. So now I'm going to rewrite this inequality. You see this inequality, I'm going to rewrite it down here. It's going to be the exact same inequality, just in factored form. So I'm going to write x minus 1 times the purple x squared plus 5x plus 6. And that's got to be greater than or equal to 0. So again, I just rewrote that inequality down there in factored form. So now we can continue to factor. So now we can see all of the zeros. And in this case, we actually don't have an even multiplicity for any of these zeros. I thought there was going to be an even multiplicity, but it turns out no. So let's do a sign chart. We have 1 and negative 3 and negative 2. Again, the spacing doesn't have to be perfect. Don't waste a lot of time trying to make a perfect number line. Okay, so let's plug in 0. Let's test 0. We've got negative times a positive, which is a negative. So that region is going to be negative. You can test all the regions and find that the signs are going to be like so, but again, you can use multiplicity to help you with that also. So now let's draw the graphical solutions. We need closed dots. And we want to know where this expression is greater than or equal to 0. So that's going to be the positive symbols. So that is the graphical solution. Now the interval solution, so we're going to use brackets, -3 to -2, union 1 to infinity. And remember, we never write a bracket next to an infinity symbol. It's always a parenthesis. So if you got those answers, excellent. Good job. Okay, so now we're going to factor by grouping. We're using all the different types of factoring that we know in this class. So first we're going to put everything on one side of the inequality, and in this particular case we can factor by grouping. In the previous problems we couldn't really factor by grouping very easily. In fact, we couldn't do it at all. But now we can take these two terms and we can factor out a GCF out of those two terms, and we can factor out a GCF from these two terms, -36. So let's double check everything. Don't go too fast when you're doing these problems, or else you're going to have to go back and fix something, which is going to be a lot of time. So now we're going to factor out 2x minus 1. I'll put that, doesn't really matter which order you do it in, but I'm going to put it at the left. So I factored out a 2x minus 1. Because this term and this term, they both had 2x minus 1s, 2x minus 1 factors, so I factored it out. And you were left with x squared minus 36, because I factored out that 2x minus 1. So now we have factored form, and we have the difference of two squares. So I factored the difference of two squares there, and we can see that we have 3 zeros. So as usual, we're going to do a sign chart. You can see that every problem today is pretty much working the same way. We have 6 and -6, and then we have positive 1/2. So let's try plugging in 0 to test this region here. And you can plug it in wherever you want, but up here is going to be the easiest. We're going to get positive 36. So we know that region is positive, and the multiplicity is 1 for each one of these zeros. So we know what the signs are going to be. But you can plug in a number in each one of these intervals into whatever expression you want to use that's easiest to find the sign of the expression in those intervals. Okay, so now we can write the graphical solution, and the expression is greater than 0, so we want the where we see the positive symbols, and that is the answer. So let's write in interval notation. And there you go. Okay, so that was a problem where we factored by grouping. I want you to try number 22. you're going to factor by grouping on number 22 also, but I believe number 22 is going to have a 0 with even multiplicity, so we're not going to have a sign change there. So you're going to want to reference 19. So try number 22. When you come back, we'll do it together. Okay, we're back. So I'm going to make a divider. Again, the first step is always to put everything on one side of the inequality. And now we're ready to factor by grouping. So we had to use the -1 rule here. And then we're going to factor out x minus 1. And then we're going to factor the difference of two squares. And notice that we have x minus 1 as a repeated factor, or repeated 0. So what that means is the sign of the expression is not going to change there. So our zeros are 1 and -1. Let's try plugging in 0 to see what the sign would be, and we get +1. And at +1, the sign's not going to change, so it's just going to remain positive. And the sign over here is going to change because the multiplicity of the 0 and -1 is an odd multiplicity. That's multiplicity 1, whereas the multiplicity over here is 2. You don't have to use multiplicities. You can just plug in a number over here, say -2, and see what you get. You get a positive number or a negative number. Plug in 2 and see if you get a positive number or a negative number, and so on and so forth. So we're going to need closed dots. And we want to know where the expression is less than or equal to 0. So that's going to be over here. But it's also going to be those dots. So we're going to use interval notation. Well, this is the graphical solution, but let's use interval notation to find the or to write the solution. And again, it's not very common to see interval notation used with one point, but that's probably the best way to write it. This is not really an interval, but we can still pretend that it's an interval. Okay, so if you got a little confused by that part there, that's okay. Now you have an idea of how to do that. So if you got that one right, good job. Okay. Now the reason that we needed this point here is because the expression can be equal to 0. We want to know the x values that make it equal to 0. So that would be 1. But these regions make it greater than 0. So that would, we're not interested in those x values. Okay, so now we're going to move to irrational zeros. If you have to find an irrational zero, I don't want you to be afraid of doing that. You don't really see these types of problems very often because they're kind of weird and tedious, but technically there are solutions to this inequality. They're just going to be a little bit more difficult to find because the zeros are going to be irrational. But again, I don't want you to be afraid of finding irrational zeros. So we're going to switch the terms, and then I'm going to rewrite, because this doesn't look like the difference of two squares, because although x is squared, it's a perfect square, this doesn't look like a perfect square at all. We're used to numbers like 1, 4, 9, 25, 36, 49, so on and so forth. But I can still find zeros. There are zeros. So I'm going to rewrite 3 as the square root of 3 squared. And now we have the difference of two squares. And how can I do that? Because if you take the square root of 3 and square it, well, squaring is just the opposite of square rooting. So they just counteract each other, and you're left with 3. So this green 3 is the same thing as this yellow square root 3 squared. So all I did is just replace the green with the yellow expression. But now I have the difference of two squares. So I can factor to x plus root 3 times x minus root 3. And so that's the only difference with this problem, really. I just don't want you to be afraid of finding irrational zeros. Again, you're really not going to see this problem very often, but if you do, I just want you to be able to do it. So let's plug in 0 and we get negative 3. So that region is going to be negative. Each 0 has a multiplicity of 1, so those regions are going to be positive. So the solution in graphical form, or the solutions, there's multiple solutions, it's going to be that shaded region there. Now let's write interval notation. So we're going to be negative root 3 to positive root 3 with parentheses because we have open dots. And there you go. You must be able to find rational or irrational zeros in certain contexts. So try 24. When you come back, we'll do it together. So remember, you're going to start by putting everything on the left side of the inequality because you want this term to be positive. So try 24. When you come back, we'll do it together. All right, we're back. So I'm now going to rewrite as the difference of two squares. 8 is not a perfect square, but I can still write it like this. So now we're going to factor the difference of two squares. And we can draw our sign chart. And at some point, you would typically rewrite root 8 as 2 root 2. But I'm not going to worry about that now. Plug in 0, we get a negative number. The multiplicity of each 0 is 1, so the signs are going to change. But you can plug in 5, and you can see it's going to be positive. You can plug in 5. 25 minus 8 is positive. You can do it any way you want. We want to mark all the x values that make the expression greater than or equal to 0. So that's going to be these outer regions here. And at this point, I'm going to change to negative 2 root 2. So that is the graphical solution. And let's write the solution in interval notation. We need brackets. And remember, never write a bracket next to an infinity symbol. Okay, so if you got that one right, excellent. Okay, so now we're going to do problems that require the quadratic formula. Again, you're probably not going to see these problems, but if you did, I would want you to know how to solve, and I should make it clear, even though you're not going to see a quadratic expression that cannot easily be factored with these particular types of problems, you're going to see it in other situations. And what's more important than anything else is just the basic concept that you can still find the zeros using the tools that you have. So that's the purpose of this. We cannot factor this, but there are zeros. And so we're going to use the quadratic formula to find the zeros. But before we do that, we should find the discriminant, because it's possible, if I hadn't written these problems, it'd be possible that this problem wouldn't even have zeros. So how do we know? Well, we just write the discriminant. So 25 plus 4 is 29. So it's a positive number, which means that there are zeros. If you got a negative number for the discriminant, then there would be no zeros. So we can put a check there. So now we can find the zeros, but again, we can't factor easily, so we have to use the quadratic formula. So let's plug in 5 for B, and 1 for A, and -1 for C. And then we can simplify. So we have -5 plus or minus root 29 all over 2. So those are the zeros. Now, when you do the corresponding problem, you don't have to write in factored form, but I just want you to understand, for conceptual purposes, that you can write in factored form, as we did in previous problems. You can actually use the quadratic formula to help you factor. We don't typically use it for that purpose. We don't think of it that way. But as you can see, we now have this yellow expression in factored form. Believe it or not, if you were to FOIL this, you would get back to that. And I would challenge you to do that if you want to try that. As long as you do the math properly, you'll get back to this expression here. Again, I'm only drawing this so you can understand the correlation between the problems that we did previously, but you don't have to write in factored form, and you don't have to write out the quadratic formula. That's just for your benefit. So now we can write our sign chart, and we're going to have -5 minus root 29 over 2, and -5 plus root 29 over 2. It's hard to see exactly what those numbers are going to be. You could just estimate or use a calculator. But each one of these zeros has a multiplicity of 1, so we know the sign is going to change. So we can just take some big number over here, maybe like 100, plug it in, and we see it's obviously going to be positive. That region is going to be positive, which means that the inner region has to be negative, because again, the multiplicity is an odd multiplicity. We have purple 1 exponents on each one of these factors. So that means the sign is definitely going to change in each region. So now we can write the graphical solution. We need closed dots, and we're trying to figure out where the expression is greater than or equal to 0. So that's going to be the outer regions. So that is the graphical solution. So I'm not going to give you a lot of those types of problems because they're kind of tedious. So let's write the solution in interval notation, and actually we need a bracket. So there you go. So now it's time for you to try one of those problems. This may look kind of scary, but it's all just review. You don't have to write the formula out if you have it memorized. You don't have to write the factored form here, and you don't have to find the discriminant necessarily, because we know what kind of problems we're doing here. So try 26. When you come back, we'll do it together. Okay, we're back. So there's the answer. Go ahead and look that over. If you got those answers, good job. Let's go ahead and go on to the next problems. Now we're going to use the last type of factoring that we're going to do today. We're going to factor the sum or difference of two cubes. And so let's go ahead and try this problem. Remember, the first step is to put everything on one side. Now we have the sum of two cubes. I can rewrite this as x cubed plus 2 cubed. 8 is the same thing as 2 cubed. So we see that we have the sum of two cubes. I can use this formula up here. The problem with using this formula is that nobody ever remembers it. So what do you do if you don't have it memorized? Well, you can just use the Rational Zeros Theorem. If there are rational zeros. It only works if there are rational zeros. That's the problem. If there are no rational zeros, or if the zeros are rational but they're fractions, weird fractions that are going to be hard to deal with, then you would want to use this formula. So that's why these formulas are useful. They work every time, whereas the Rational Zeros Theorem may not work. But in this case, it's going to work because we can see that there's going to be rational zeros. We can plug in -2. We see that's going to work immediately. But let's just follow the motions here. So I got that number from there, and I got that number from there. Okay, so let's try 1, but if we try that, we know it's not going to work. Try plugging in 1, we get 9, that's not a 0. Try plugging in -1, we get -1 plus 8 is 7, that's not going to work. Let's try plugging in 2. We get 2, we get 8 plus 8 is 16, that's not going to work. And let's try -2. That's going to be -8 plus 8 is 0, so that does work. That is a 0. So now we can divide x cubed plus 8, which is going to be 1008. Be very careful that you write this correctly. We need those spacers, those zeros. We're going to divide that by x plus 2. Using synthetic division. The remainder is 0, so that's a good sign. So now we're going to take this expression up here and rewrite it down there as x minus 2, actually x plus 2, times the purple x squared minus 2x plus 4. So we just rewrote that inequality. Okay, so now we can see one of the zeros is -2. Now we want to factor this, but it doesn't look like that's going to be easily factored. To figure out whether or not it can be easily factored, we're going to use the discriminant, and there may not be a 0 at all. So we'll have -2 squared minus 4 times a times c, and we get 4 minus 16, which is negative 12. That means that there's gonna be imaginary zeros for this factor, which means that there's only one real zero, and that is negative 2, which we get from here. With this zero here, we use a discriminant to find out that there are no zeros there. So now we can use the sign chart. We can plug in 0 to test this region, and we get positive 8. So that region is going to be positive, and the multiplicity of this 0 is 1, so the sign definitely has to change. But you can plug in negative 3, and we see we get a negative number. That would be negative 19, I believe. So now we can go up here, because we're out of room, and we can draw the graphical solution. So we want to know where it's greater than, where the expression is greater than or equal to 0. So that is the graphical solution. And if we write the solution in interval notation, it would look like this. All right, so there you go. So in that case, we have the difference of, or the sum of two cubes, and we use the Rational Zeros Theorem. But you can see that memorizing these formulas would be very useful in that case. We could have done the problem a lot faster if we had just memorized those formulas. Now this problem up here, using the Rational Zeros Theorem, is not going to be very practical, because it turns out that the 0 is going to be, whoops, that should be a cube. Turns out the 0 is going to be a fraction, and it's going to be a little difficult conceptually to test it. So in this situation, we're going to use the formula. So first we need to identify A and B. So to do that, we're going to rewrite the expression as 5x to the third power minus 6 to the third power, and now you can see it's the difference of two cubes. A is going to be 5x, and B is obviously 6. So I just wrote that blue part there, you see that? And then I'm going to write a squared, so 5x squared minus a times b plus b squared. So that is just a different way of writing that purple expression up there. Okay, so now we have 5x minus 6 times 25x squared minus 12x plus 36. So we want to know if we can factor this, or we might have to use the quadratic formula. We just need to find the zeros. But we don't want to do that unless zeros actually exist. So we're going to use the discriminant to help us determine if zeros actually exist, and to see if the zeros are going to be able to be found by factoring rather than using the quadratic formula. So we have negative 12 squared minus 4 times a times c. So you can tell that those numbers are pretty big. Looks like that's going to be 144 minus 3600. So that's going to be negative 3,456. So it is a negative number. What that means is there are no zeros that exist. Well, there are zeros, but they're imaginary. So imaginary numbers don't really exist on the number line. So that means that we only have one zero, and that is 6/5. So let's test the regions. Let's test 0. We get a negative 216 when we plug in 0 for x. So that region is negative. If we plug in 2, we get a positive number. But again, you can use the multiplicity of this 0 to understand that the sign changes. So now we can write our graphical solution, and we want to know where the expression up here is less than 0, so that is this region over here. So that is the graphical solution. Let's write the solution in interval notation. And there you go. So I want you to take a picture of these problems along with the formulas for factoring the difference of two cubes. And I want you to use that information to help you to do problem number 29. So when you come back, we'll do it together. Okay, for this problem it's best to use the Rational Zeros Theorem. As you can see, if you got those answers, good job. Go ahead and try number 30, and when you come back we'll do it together. So here's the answer. If you got that answer, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3, number 4, number 5, number 6, and number 7. But don't go before you get your homework. Let's take a look at the homework. Here's a screenshot number 1 of the homework, and screenshot number 2, and number 3, and here's the answers. Remember, it's not enough to attempt the homework. You must do it completely, correctly, and neatly, and keep it in order in your binder or your digital notebook. So get that homework done, and I'll look forward to seeing you in the next class.